That little yellow thing up there says I'm recording, so hopefully, I think it maxes out at a certain point, but let's see. 1.3, properties of graphs of functions. The new words that we were talking about were increase, which is up to the right, and decrease, and down to the right. Okay? Phones and stuff should be off your desk. Get used to that habit. Off your desk, not in the corner. Bag, not pocket. Just get it away so you can't even think about looking at it, even if it vibrates or whatever. Okay, so it's completely out of your view. Now, when I talk about increase, what I always say is do this, right? So cover up the arrows up to the right. It's not the direction of the arrow. People go, but it's up to the left. No, 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 no. I'm not talking about, this is a mathematical definition. So mathematical definition is that as you go to the right of the graph, as x increases, y increases. So that's not looking at where the arrow is going. So cover up the arrow, that's decreasing. This line, increasing. Don't follow the arrow. Okay, so increase, decrease. So the way that I want you to write this, so let's correct this part here. So right away I needed to correct something. I want you to write this in a more mathematical way. So this is the way that it's defined in your brain. So this is wonderful, 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 wonderful. That's my brain thinking that. I don't want you to write that anymore. I realized afterwards I want you to write it in another way. I want you to write it like this. As x, and you're going to put an arrow. The arrow indicates approaches. As x approaches infinity, which means to the right. So that's to the right, comma, y approaches, as x goes to the right, y approaches up. And so instead of up, I want you to say infinity. Right? So as x goes to the right, y goes up. This is the way I'm going to be writing it for the rest of the course and in calculus. So whatever you're learning here, if you're taking the calculus course, we're using the same notation. Okay, so I want you to be able to write it this way. For an interval of decrease, what you're describing as it's down to the right. That's what your brain is thinking, but the way you're going to write it mathematically is you're going to say as x approaches infinity, which means to the right, comma, y approaches, and then instead of down, negative infinity. So as x goes to the right, y heads down. So this is your brain thinking that, and this is you writing it like a grade 12 student, right? So in grade 9, we would write it like this, up to the right, and to the right, that sort of stuff. But now in grade 12, we want to use the math symbols. So you're using the arrow saying approaching. That's where it's heading. An odd function, we talked about this. There's two different ways to look at an odd function. One is that a horizontal reflection equals a vertical reflection. So the horizontal reflection equals the vertical reflection. That's one way to look at it. So that means that when I had this little line here, right, I took that line and I horizontally reflect it, which means it goes here. Okay, we see where it is? If I had that original line here and I vertically reflected it, it would do this, which was the same line. So they're equivalent, equal to each other. That's one way to understand what an odd function is. The other way, this one here, is a double flip. So you say, okay, if I horizontally reflect it, which is this negative, in the x means horizontal. So if I horizontally reflect it, it does that. We're good with that? Okay. Then if I take my answer from here and I reflect it again, so I take my answer, this orange here, and then I flip it vertically, so it does this, it goes back to the original. So it goes back to the original. So a double flip, so a horizontal and a vertical, compares back to the f of x. I lost my second bracket here, so the f of x. So if it goes back to the f of x, that means it's odd. So that's the definition of odd. They call it symmetrical about the origin because do you know what it looks like? It looks like we twisted it. It looks like we put our pin in the middle like it's a clock and we went whoosh and we spun it around. So if you spin it around, that's why they say symmetrical about the origin. It's harder to picture that visually, so mathematically they went, it's a double flip. Reflect it 2 times or compare the 2 reflections. So we'll come back to that now in a second. And then even function was that if you put a horizontal reflection, it equals the original function. So a horizontal reflection equals the original function. That's what that notation is saying. So the horizontal reflection equals the original function. That means it's symmetrical about the y-axis, which means, look, it's just a straight flip. It's the same thing on both sides. So flip, flip, flip over. It's exactly symmetrical about the y-axis. That's an even function. The original names of it came from the exponents. They noticed that this happened with the y equals x squared, right? And the y equals x, which has an exponent of 1. So it's odd and even. That is mostly the pattern that you look at the exponents, but it's not exclusive to that. So just because it has a power of 2 doesn't mean it's going to be even. We know that because for a parabola, say, right, we know a quadratic, as soon as I shift it here, right, it's still x squared, but if I shifted it to the right, is that an even function? No, because my symmetry line is no longer y. So just because it has a squared in the equation, right, doesn't mean it's going to be an even function. But it is one of the characteristics, right? So you go, wait, it did come from that, but then they started shifting things around, right? So that's where the even odd names came from. And then they said, but you have to look, because not everything squared is going to be even. Not everything odd will be odd. Okay, so then we do the mathematical check, which we're going to do today. All right, so that's even, odd. That's the definitions. Continuous function is any function that does not contain any holes or breaks over the entire domain. There's holes and breaks. Asymptotes is a break, right? Because you have to break to continue to another asymptote. It's where you never lift the pencil. So again, in layman's terms, in your brain, you're thinking, oh, so I never pick up my pencil. No, the whole graph you can draw in one stroke, technically. Now, that's continuous. We're going to come back to that definition as well. Otherwise, if there's a break in the graph, and again, I wrote this wrong. Otherwise, a break in the graph is called a discontinuity. Okay, so it's discontinuity. There are 3 types of discontinuity. I made a mistake there and I said point discontinuity. It's not necessarily a point. There's point, infinite, and jump discontinuity, which we are going to explore either in this course or the other one. I'm getting the 2 courses mixed up. I know we definitely do it in calculus. I can't remember if we introduce it to you in here or if we just say discontinuity here and then continue this in calculus. I get the 2 courses mixed up. Okay, but it's not a point discontinuity. There's actually 3 types, right? So it is a discontinuity, and then we discover which type later on. Okay, so wherever you have to lift up your pencil, it's a discontinuity, and then we'll look at the types later on here. Then I just talked about, again, the names. So linear, you have to know the names now. You got to say, be able to use the words when you're saying these ones. So sine, quadratic, linear. We know the basic functions, right? We covered this last class. We filled this in. And then here, the absolute, the square root, the reciprocal, the circle. We always label and show dotted lines for any asymptotes, always, always. Right, so always do that. Okay, and the circle. The circle is not a function, it is a relation, though. All right, so we know all those. And then we started, did we start? This is our note, right? Yes, we started the substitutions. Let me just walk you through it one more time, especially if there's anyone new who wasn't here for the lesson. So for example 1, so step 1, I was always checking the horizontal reflection. So I sub in this. You do not have to write step 1, step 2. So whatever's in these little bubbles, you don't have to write. Those are just kind of your brain thinking. Step 1, I check the horizontal. I plugged it in. You look back at the original. Again, you don't have to draw the face. You look back at the original. It's the same. So then you stop there and write your conclusion. I always want you to write a proper conclusion. I want more explanation, not just even. Okay, I want you to say, since the horizontal reflection brought me back to the original, that's why I concluded it's even. So give a bit more explanation, not just the word even. Okay, so not just the word even, explain, then even. Now, that's if it's even. If it's odd, then we checked it first for negative to see if it was even. We said, oh no. Once you see it doesn't match, I want to see this conclusion, okay, since the horizontal reflection did not bring me back to the original, therefore it's not even. Okay, I want you to state that. So again, I don't want a jumble of calculations conclusion. I should be able to flow. It's like a story. Honestly, when I read it, I should be like, good, 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 done. Right? I shouldn't pause. Anytime I pause reading yours, it's like, what? Oh, that's not good. That's probably where you're losing a half mark or a mark. Right? So I should be able to go, oh, good, wonderful story, excellent. Oh, that's what happened at the end? So you're telling me the story. I should be able to just read from beginning to end. So this is what I checked. This is what I concluded. Step 2, you don't have to write step 2. I put another negative in front of here, so I'm telling you mathematically what I did. I put a negative in front of that answer, grab that, so show me what happened, simplify it. Oh, I noticed that it was, you don't have to show the eyes. I look back here. Then you said, oh, look, since my double reflection brought me back to the original, I concluded it was odd. So it's flowing. The story flows, easy. I read from top to bottom. Questions, clarification. Okay, next page. Okay, so for this one, so I didn't write the steps from now on, right? Because I said you don't have to. So what I would do is I just start with the first one. I tried the negative, plugged it in. It became the original, so I went right to the conclusion. It's even. Here, I put the negative in. I'm going to emphasize this one more time. I do want you to simplify whenever possible. Not everything can be simplified, but if it can be, I want you to show me your beautiful math understanding that if a cos function is horizontally reflected, it does nothing. So the cos of negative x was equal to cos of x. Because a horizontal reflection ended up doing nothing, that's where this came from. So wherever possible, do a simplification. Sometimes you can't. So if a horizontal reflection or a vertical reflection doesn't change it, you can't simplify it. So don't force it, but when you can, I simplified it. So I said horizontal reflection is back to my original. I'll just write it as cos x. Okay, and again, that's you showing me your trig knowledge. So whenever you can, you want to do that. So plus 2x, I looked at it. It is not the original, so I concluded not even. Okay, then I took my answer here. I stuck a negative in front of this answer here. I grabbed it. You don't have to show the highlight, but that's what I'm grabbing here. I put the bracket around it to show, to emphasize, brought the negative in, and then I went, oops, looked back, still not the original. So I said, therefore it's not, oh, that's a mistake, isn't it? What should it say? Yeah, odd. Thank you. See, you should always double edit my stuff. So not odd, so stop me if I'm wrong. So stop odd, therefore neither. And I know the neither part is kind of redundant because you just said not even, not odd. But usually the question, I think it said, describe if it's even, odd, or neither. So I'm just trying to make sure I really answered the question. Therefore neither. Okay. Questions with that? Okay, let's do any corrections if I have any. Then here, I put the negative in. I got that. I said not even, right? Here, I put a negative in front of the other answer, and I went, oop, it brought it back, so therefore it's odd. So it did bring it back. I tried it again, right? Put the negative in. It's not even. I put the negative in front of that answer, and it's not odd either. It did not bring it back. And you can even picture the graph, right? And then I said neither. Any questions with that? Remember that, not even, not odd, neither. Okay, so no questions. Sorry, we did this one last day, so we're good. Okay. And then over here, we have what I put the negative. Okay, and one more time. So where I put the check marks, emphasizing this again. You have to simplify where possible. So simplify where possible. Okay, so simplify where possible. So wherever you can, I want you to simplify. So this part here, I want you to simplify that because you can factor out and cancel out the negative. What that means is, so think about it this way. Okay, it's like the sine graph or the cosine graph I had above. I have the absolute value function, which looks like this. Okay, and what I'm saying is that y equals the absolute value of x and y equals the negative, right, the horizontal reflection, those are the same. They're the same. They are equal. So then that's where I said if I have the negative, I'm just going to simplify it to x. Right? So I said, I know that this is the original. I did a horizontal reflection. Nothing happened. And that's why I said the horizontal reflection is equal to the original. So we're good to go. Yeah?
If you get rid of the negative, why do you keep it distributed to the 3?
Oh, because when you factor out, so remember how we said whenever you do a transformation, you have to take out the negative from that so that you're not reflecting your translation. So by factoring it out, I fixed it so it wasn't heading the wrong way, right? It wasn't heading right versus left. So I took that away so the reflection is no longer there, and that means that the graph was actually shifted to the right 3. Think about the graph. So think about the graph. If I was to graph this, okay, to graph that, where would my starting point be? Where does it equal 0?
Negative 3?
Nope.
Like what do you mean?
Where do I put the starting point? So my V, this point here. Where's my vertex?
Wouldn't it be at negative 3, 0? Or sorry, factored out, so it'd be positive.
No, you don't even have, yeah, and that's why I'm saying factored out. If you put in negative 3, look what happens, it becomes 6. So what happens? You have to factor it out so you know it's positive 3. So that's what we're trying to do here is we're saying, train yourself to factor it out because otherwise, look, you wanted to say negative 3, but when you put negative 3 in there, you got 6. That's this point over there. It's not, it's way over here, right? So that's why factoring it out fixes it so you're only looking at the translation separate from your reflection, right? So that's why. So without factoring it out, right, you were going to put the wrong number, negative 3. It's not that. This was affecting, this affects your translation. So that's why we said last year, always factor it out because this number affects your translation. So once you factor it out, then you can say it's at 3. Okay, so that's why always factor it out because otherwise it's affecting your translation. Make sense? Yeah, that's why. And mathematics is just because otherwise you're affecting your translation with that sign in front. Same with the number. If there was a 2, you'd be affecting your number as well. So whatever it is, you have to factor it out so that the translation is separate from the stretch or shrink or reflection. Okay, so then there, so that's why you have to simplify it. Then I tried the odd and it was neither. Here, when I factored out the negative, which I didn't have to factor out because it was just attached to it, but when I got this part here, that negative there can cancel out because a horizontal reflection cancels out, which made me realize it was even. So if you did not factor out that negative and cancel it, you wouldn't see that it was originally back to the original function. Okay, so that's why you do have to do the simplifications. You have to understand the transformations now, this year, so that where you simplify, it does affect things. Yeah.
It's positive because, like, if you were to put any number and you do the absolute function, it stays positive.
Yes, it takes it right off again, so it cancels it out. Yeah. Okay. Last year we let you just do the horizontal reflection, but some people would be like, "But doesn't that do nothing?" And we were like, "Yeah." So can I skip it? Yes, you can. We didn't make you do it because you're just getting used to it. But this year, I need you to understand the math of it because otherwise, look, mathematically, you can't finish it. You go, it's not the same. So if you stop here, you go, it's not the same. But it is because that reflection did nothing. So after you've graphed it a bunch of times last year, hopefully you're going, wait, I can see now it's doing nothing. So that's why it takes it away because you're canceling it out when it comes out of that absolute anyway. So this year, we kind of want the higher understanding of that. Okay, because it cancels it away, so it becomes that. That's why you can conclude this now, right? So it takes last year's information and adds just a bit to it. Okay. All right. So that's that. Next page. No more clarification. Good. Next page. So let's try this now. This one here, I asked everything just to kind of summarize everything we've already covered. So we're doing increase, decrease, odd, even, neither. Right? Continuity, equation of asymptotes, and end behavior. Everything. Everything that we covered so far, we're going to look at in this question. So let's start with the increase, decrease. We'll save the odd, even, neither for the end just because we just did a bunch of those. So that's okay. And continuity and stuff like that. So let's start with the increase, decrease first now. So increase, decrease. So start with the increase, decrease, and I'm going to say, now, if you can picture the graph, you're very welcome to picture the graph. They tend to ask you a lot of familiar from the 8 functions that we learned last year, so that whenever you can try to picture the graph. Use your grade 11 knowledge to do this. You're not to purge it and say, I only do this way. You're using your grade 11, so it's not bad. So I'm going to just draw it, right? So let me do a rough sketch of it so I have an idea of what it looks like. So I know that it looks something like again, just a rough sketch. I'm using a ruler just because I find that my hand shakes otherwise, so I want to make it neater for you guys. So here, we've got this function. The negative means a reflection. It's in the middle. It can be horizontal or vertical, so it doesn't matter which way. The 3 is a stretch. The stretch is not going to affect the increase, decrease, or continuity, so I don't care about that. It doesn't have to be a good, perfect graph with points and everything, mostly just the shape. Okay, so I'm not going to do the 3. But the 4 is going to affect stuff, so I'm going to do 4. Again, you don't have to do with ruler. I'm just doing it so that my graph is neat for you guys, like that. So it hasn't shifted left to right, so I'm going to do this. So then I know it's reflected, so it looks something like this. Again, I'm trying to do it neater so that you have something to look at. So that's your brain going, okay, it's upside down, right, reflected, horizontally or vertically, equivalent. It's moved up to 4, so this is y equals 4, and other than that, no. All right. Then, I want to talk about increase, decrease. Again, I know I say draw the arrows on it, which you're supposed to, but cover up the arrows when we're talking about increase, decrease. When is this graph going up to the right? Yeah. All the time except, yes, that's it. All the time except 0. So up and up. Again, don't follow the arrow down. Don't do that because people are like, but it's going, no, cover. It's always up to the right, up to the right. Okay, it's not the direction of the arrow, it's the slope of the line. Up to the right, okay? So it's increasing everywhere except not 0. So let's write that using our beautiful new interval notations. We're going to keep practicing that. So we're going to say increase, and this will be when x is, and we're talking about, you always describe the x value for the increase, decrease. Where is the x increasing? So you're telling me the domain. So we're going to go from negative infinity, comma 0. You can use the symbol or you can use the word or, right? And then from 0 to infinity. So negative infinity to 0 and 0 to infinity. So you can use the word or the symbol for or, union. Okay, round bracket, I'll just emphasize that. Remember when we learned our notation? It's round on both because it's never going to touch at 0 because it's an asymptote. So round on both. Decrease, we're just going to say none. Okay, none. There's no interval of increase, decrease, so I just said none. There is no interval of decrease. There's no interval of decrease. There is an interval of increase. All right. Odd, even, neither. Let's do that in a minute. We'll try that one here, the odd, even, neither, in a second. I want to go on to the new stuff, right? So that we'll do odd, even in a second. Continuity. So continuity for this one here, continuity means where do you have to lift up your pencil, right? So I can draw that whole side and that whole side, but it's split here in the middle. Again, when you're talking continuity, you're talking about the x value. So describe the x, the domain of it. So we're going to say that it is, now it says continuity. It doesn't specifically say tell me where it's discontinuous or tell me when it's continuous. It's just saying continuity. So you can answer this question in 2 ways. I would accept it either way. So you're either going to say continuous, tell me when it's continuous, when x goes from negative infinity to 0, or from 0 to infinity. So you either say that, or you could say that it's discontinuous when x equals 0 is fine, because it's a single value. You don't have to use an interval notation at all. You just say x equals 0. Okay? So if I just say discuss the continuity, you can just say where it's discontinuous and state the points. If it's a domain, then you want to say the whole domain. So if it's discontinuous from here to here, but here it's just a point, so just do x equals 0. Or you can say it's continuous along this domain. Okay? If I say continuous, you must answer it this way. If I say where is it discontinuous, you must answer it this way. If I just say discuss the continuity, either answer is fine. Okay, so if I'm specific, read the question. If I say where is the function continuous, you must say where it's continuous. If I say where is the function discontinuous, you would state there. And if I say discuss the continuity, both answers are fine. Either answer, and not both. Is that your question? Okay. All right. Okay, so continuity. Equation of asymptote. So I'm just going to do, and usually on a test, sometimes we give you a chart to fill in or fill in the blanks so that you don't have to go, which answer am I doing? So it would make it more organized, but I'll just do this. So continuous, so what do we got? What do we got? Equation of asymptotes. So my vertical asymptote is this one here, which is going to be at x equals 0. And we're still using VA. I think you used that last year as well for vertical asymptote. Right, you've seen that before, VA. Okay, and then HA is this one here, y equals 4. Okay, equation of